Welcome, everyone. Thanks for joining us tonight. My name is Artem Kuzin, and I'm head of data engineers at the Social Discovery Group. In case you never heard about our company, I'd like to share a short presentation about us. Social Discovery Group is a global IT company focused on connection people, solving problem of loneliness and isolation with the help of digital reality. We have more than 250 million users from over 100 countries, which send 75 million messages daily. Our international team contains 700 professionals and digital nomads. What is social discovery? Besides it's part of company name, what does it mean? For users, social discovery is about finding people on the web and communicating online and offline. But in fact, the market is much wider than it seems. It combines technology services that help people expand their social and business connections, such as social networks, dating apps, games, training, and travel platforms. Our products include dating apps operated by Dating Group and new social entertainment apps built by SDG Lab. In SDG Lab, we developed services based on new principles of communication with a focus on video streaming, AI technologies, and game mechanics. Among our products is a Magnet. It is a social game, social discovery game and dating app where you can communicate on a deeper level and discover personalities first, not their looks. The user can generate a cartoon avatar and fashion their digital identity. Another wonderful app that I should mention is a Journey. It's completely new form of human-AI relationship that also was created by SDG Lab. This is a virtual companion who can become a friend or even a romantic partner of the user. It is able to hold the conversation, empathize, support, and even share its feeling. Please feel free to join our community to learn more about social discovery. And let's move on to our first speaker, Alexander Piskotin, with a presentation about demand-side platform. I hope everyone know MES because next slides will contain some hard stuff. Please welcome.
Once again, thank you, Artem. Thank you, everyone, for coming. My name is Piskotin Alexander, and I'm an ML engineer at the Social Discovery Group. So my speech here today is about our in-house demand-side platform, or DSP, that we are building. And specifically, it's about the bidding algorithm of it, and you could say that it's about the optimal bidding problem or optimal bidding strategies. I'm not going to talk here about the DSP, the whole DSP, since it's too big and complicated, and I'm not responsible for developing the whole system. And the more of it, I'm not responsible for talking about it. So today is just the ML engineer's view, optimal bidding problem. Before we start, there is some quick disclaimer. If you are not familiar with the terminology on this slide, I'll spend a few seconds here to make it clear. So there are mainly two types of marketing strategies. Prospecting is the marketing strategy where we are attracting new users or that we never met before. And the remarketing is the marketing strategy, the goal of which is to return our customers that are already familiar with our products, and moreover, we are familiar with these customers. So, okay, a few seconds here too. The DSP is the part of the system that is called ad network. The ad network is actually like the communication of the main two parts, which are the demand side and the supply side. Speaking about supply side, it consists of the user, the one to see the advertisement, the publisher. It's like any business on the internet that wants the advertisements to be shown on the website, mobile app, or whatever. And there is also a supply side platform which aggregates these requests from publishers, so it makes them efficiently communicate with the demand side. So, speaking about demand side, there is advertisers, which are literally us. We want our advertisements to be shown on the internet, and we are using demand side platform, or DSP, which is like a complex tool specially made for communicating with the supply side. So there is also an ad exchange and data exchange platforms. Mostly they are providing the data to the both sides to make it communication, make the exchange more efficient. All right, so as I said before, there is just an ML engineer's view on the problem, so we can stick to some simpler scheme to follow. So this scheme here is rather typical for any like machine learning based solution that is running like in real time. So the input is the bid requests, which is the data about the auction. This input goes to the bidder. We call it bidder. So it consists mainly of two parts: the bidding algorithm that makes the decision what the bid is should be, and the splitting system, so we could test our algorithms against each other. And the output is bid value itself. So as we are speaking about some data-driven solution, we are communicating with the database that contains like auctions history, wins conversions, campaign settings, and so on. So we could feed our models over this data and to make some analytical reports to marketing specialists or traders, speaking in terms of real-time bidding. All right, a few seconds about the real-time bidding auctions to make it clear why the optimal bidding problem is like a really hard problem to solve. Firstly, there are first price auctions and second price auctions. First price auctions, in the first price auctions, the one who wins the auction pays the price equal to the first largest bid, which is actually the bid that the winner has placed. In the second price auction, the winner of the auction pays the price equal to the second largest bid. Mostly on the market, like today, almost all the SSPs are conducting the first price auctions. All right, so the next point here is that the communication with the SSP is like real time. So on average, the timeout for every request is about 300 milliseconds. So it includes everything from the network latency. It includes some filtering on DSP and SSP sides both, and the decision making itself. The next property is that the data provided for every single auction is like really limited. It's called bid request, and I will show it on the next slide. All right, there are like thousands of SSPs, thousands of DSPs, millions of publishers and advertisers, trillions of impressions by day. So it's like a multi-agent, continuously changing environment. So there is no silver bullet solution. You always have to compete with other participants. And the most important property here is that there, firstly, we have no information about the distribution of the bids for every single auction at all. And the second one, you have no information about the winning bid. Only in cases when you have won in the auction, then you have obviously the information about the winning bid. But in any other case, there is no data. So speaking about limited data, this is the typical bid request that we are receiving from the SSP. In red, I have marked some crops of somehow useful data that is provided. So there is there are some metrics that are provided by SSP. You see there like CTR, but its value is 0, and mostly those metrics are actually 0 or missing. There is also some information about the publisher. It's the exact page, it's the domain, it's the language of the publisher, and maybe something more. We have some information about the device the user is using. It is a user agent. It is the IP address. It is some geo information, maybe country. And mostly that is all. That's all we have. So on this data, we should predict some optimal bids. All right. So speaking about our experience, we have conducted several experiments. It's like 7 experiments in the 4 months, which is quite impressive, I suppose. Some of them were a huge success. Some of them were not. Here we are going to dive a little bit deeper on the algorithms that we have been using. All right, so the first solution to this problem that could come to mind. Well, every ML engineer is good at building some classification models. So why don't we use this approach here? Starting with remarketing, our only goal is maximizing the number of clicks. So we just predicting the click probability and using some threshold. If the probability is lower than threshold, we are bidding 0. We don't participate in the auction, or we are bidding the value B. Value B is provided by the trader. So simple as that. The issue here is that varying the threshold, we can control a number of bits, but we do not control bits value. So the next solution that we came to was that to vary the bit itself, we are not sticking to some classification model, but we are using the raw probabilities of click. So now the action space of our problem is like continuous. So simply we take this value B provided by trader again and multiply it with the probability. So now we have encountered with another problem. Expectation of click is less than 1%. So we are having like really low bits without any way to control it. And the solution here should be some control, taking some control over the multiplier value. So take a few seconds here to look at the calculations. There is no like words spoken from my mouth that could better explain what is written on the slide. The principle here is that we are using simple math. We are using like our knowledge about the distribution of impressions and of probabilities to calculate the multiplier that we want to use based on the daily budget. I suppose it is not clear from the slide. Maybe you could come up with the question right now. I will answer it after the speech, or you could directly message me on. I will share the context at the end. All right. So speaking about this algorithm, we call it adaptive multiplier. We have actually really improved our algorithm. It works surprisingly well, but the problem here is that it just something like just an engineered solution. We don't have any mathematical proof that these bits that we are making are something like optimal bits. Could we do better? Could we directly learn optimal bidding? All right. So after some research, we came up with another solution. So the algorithm called CATS, or Continuous Action Tree with Smoothing. It's available on the Wopal Webbit package, and it's totally open source. And you could use it with some like Python or something, some other languages. All right. So what's about this algorithm? It seems to be some like simple decision tree, but it's not. So what are the properties of this algorithm? Firstly, we are learning maximization of a cost function of any nature, whether it's differentiable or not. It's called cost-sensitive learning. Secondly, this, as we can still speak of it like it's a decision tree, this decision tree makes the classification of some classes. The classes are represented by the n, which is a parameter of the model, n points evenly distributed over some segment from A to B. On the picture you are seeing, it's the segment from 0 to 1. All right, so the setup here is similar to the contextual bandit setup, and it's again some classification setup, but we can distribute the loss for a single leaf over the neighboring leaves, and in this way we get advantage of our the continuous action space, which is actually the one of the properties of our problem. The next advantage of this algorithm is that it provides us with a bottom-to-top learning. The base algorithm of the CATS is actually a filter tree algorithm. And the advantage of this algorithm is that it can learn over the single examples rather than batch training over and over from scratch. All right, and the last but not the least point here is that the nodes of this tree are actually linear models. So it complicates the model, so you can learn some sophisticated patterns from the data provided. It is rather unuseful when we are talking about the classical decision trees, because decision trees tend to overfit much. but we are like in the online learning setup, so it isn't really a problem. All right, so how could we use this algorithm? So the simplest solution is just to remove the probability model and replace it with the CATS algorithm. Speaking about the CATS, the main part of the algorithm, of course, is its cost function. It could be represented. It could be represented with the in the form of a reward function or the loss function. The loss function. The main difference here is just a minus sign. So speaking about reward, it's rather like straightforward. If we have no impression, the reward is 0 because we haven't lost any money, and definitely we have not benefited from it. If the impression is, if there was an impression but there were no click, then the reward is minus a bit. So a reward is equal to the money that that we lost. On the other side, if we have an impression and we have click, which is our goal, then the reward is 1 divided by the bit value. So that means that the lower the bit with which you have won in the auction, the higher is the reward, and the connection here is non-linear. All right. We have implemented this, but we encountered with another issue. So the problem here is just that the model learns badly. That is because that the actual bit, the final bit, consists of 2 parts: the value given from the CATS algorithm and the multiplier that is given by another algorithm that the CATS knows nothing about. So it's the reward function then is like really noisy, or you could say random from the model's perspective. So a model learns over some noisy data, and we have some noise on the output. So the next solution, obviously, is to get rid of this multiplier and directly make the model predict the bit value with the same cost function. Now we encountered with another problem. So like getting rid of this multiplier algorithm has now no human feedback or no control. It doesn't know anything about the budget we want to spend. So that's the problem, because the algorithm learns some like optimal point. Whether it's too low or too high, it doesn't matter, and we can't control it in any way. And another point is that the cost function by itself is wrong, and I could explain why on the next slide. So in the next iteration, we have come up with the like upgraded reward function. Look at the equation. We simply just added the parameter S0, which provided with some huge improvements over the model. So firstly, the parameter S0 is actually some risk control parameter. So the lower values of the S0 provide the model with the greater losses over the impressions with no clicks, and some lower payoffs if there was a click. So the lower the value of S0, the more the model is conservative. On contrary, the higher the value of S0, the more the model is risky. The second huge success here is that if we recall the reward function on the previous iteration, we could see that we are summing the like bits, which is dollars, and the inverse dollars. And any like physician or mathematician or any person that uses the math properly could kill us for that, because the output, the measurement of output is like unknown. So speaking of the version 2 of this reward function, the risk control parameter is obviously like the having the dollar measurement. So the summation now is valid. And the first like a very important advantage here is that the reward function now looks like really symmetric, like really nice and beautiful, and that's some hint that we are doing something right here. All right. So after some successful iterations over the remarketing, we came up with the idea that the remarketing is not what we are looking for. There are just two very small audiences that, and the remarketing solution is just it's just the value of this solution is just too small to make any efforts improving it. So we had to, there was a business solution made that we should switch to the prospecting. Well, what does it mean for us, like ML engineers solving some ML problem? Firstly, RPS is much higher in prospecting. While in remarketing, you have like upper limit of like 100 RPS. Moving to prospecting, there are like no upper limit. You are starting with some like 100 requests per 1,000 requests per second, and to have a little bit of conversions a day. So it means that you should spend some time preparing your algorithms to work with the load like that. Another problem here is that while we were doing some remarketing, we could stick simply to the clicks as our goal conversion, because we know who are the customers that we are showing our advertisement to. We are sure that they are like real people. But moving to the prospecting, it's like moving to the wild internet, where there are like click bots, fake publishers, fake users, and so on. And that means that we should use some rather higher like conversions, I know, like registrations, like first sales, and so on. And that leads us to smaller conversion rates and longer feedback loops in time scale. And the third problem here is that having these many conversions, the cost function now is a simple linear combination of conversions with some weight. Of moving to this simple linear combination from the some like skated solution we had in the remarketing is quite sad. All right, and here are some things that we haven't tried yet on our algorithm, but I suppose they could greatly improve your predictions and your bidding algorithms. Firstly, almost all useful data in the bid request is categorical. So you could improve your algorithms if you encode this data well. And it can be dealt with some algorithms like matrix factorization, for example. You could also use some additional models. like click prediction, click probability predictions, conversion predictors. Like you could directly forecast the winning bid. It's rather tricky, but it could be done with some accuracy using the same tricks that you are using in the churn prediction. And the last point here is that you could use lookalike modeling. What's it? Well, while you only have some like target data, the winning bid only when you participate and win in the auction, you anyway have huge loads of these bid requests that are like raining on you. So simple as that. You are able with some accuracy track a single person here over these bid requests, and like enrich your current auctions data with this historical data over the user or the publisher. All right, thank you very much for your attention. That's all. That's all.
Nice job, Alexander. Awesome presentation for tough topic. Audience have no questions, but I do. You have mentioned that from remarketing to prospecting caused you many technical troubles. How did you solve it?
So speaking, thank you for the question. So speaking about these like technical troubles, I would start with what are those like technical troubles. The first thing is that I said that the RPS is much higher, so we have to make our rather small algorithm of bidding, which includes like only the connection to the database and the algorithm itself, and like the learning over time. We had to divide this small algorithm to the smaller parts, making some like microservice architecture to be available to cover all these like thousands of RPS. And the another problem was that using Wopal Webbit package is rather tricky. It has like a very unique API, and this makes it like really problematic to use it. Because there are not much like answers on the Google or Stack Overflow, and we encountered with the problem of the leaking memory, and we just couldn't solve this problem with the like standard methods of tracing memory, and we spent here quite a lot of time.
Maybe next time you should try to make your own algorithm and maybe send it to Stack Overflow to help other.
Good idea, thank you.
Thanks, Alexander, again. I suppose a lot of experience I gained during this project. And thank you all for joining us tonight. It was a pleasure to share our experience. Hope it was useful. Stream will remain here on YouTube channel. Hope to see you again. Have a nice evening. Bye. Sorry, we have another question from Sergey Kozlov from Prospecting users. Why do you decide to create your own DSP and bidder rather than using existing one from the market? For example, IP on web.
All right. So thank you for your question. The main reason why we have started this this project is that these DSPs that are provided on the market are gaining some extra fees over all the budgets that you are spent through them. So the main problem we were trying to solve is to make the optimization and make these costs to stay in our pockets rather than spend to the other businesses.
Sergey, I hope Alexander answered is okay for you. And another questions from Valentin. What kind of type of big data is analyzed in your algorithm? I think the answer was in presentation. You show us the bid request. It's all that you have. Am I right?
Yes, thank you, Artem, for carefully listening my presentation. Yes, these are just the bid requests, the huge loads of it. You could say that it's big data, but it's a rather not so simple answer to a question to ask what is the big data and what is it and what it's not. Mainly, the input of our model is just bid requests and many lots of it.
Maybe to impress our audience, you can share some counts of bid requests that you use to fit your model. It's milliards, thousands of millions, petabytes also.
So you could say that starting with the 10 requests per second, you have 600 over the 1 minute, and 36,000 of in hour. So in the one day, over the 1 day, you are having almost 1 million. So our algorithms actually built over the million of these examples a day.
I think that's enough. Thanks everyone again. If there is no questions, we can say goodbye again. Thanks everyone.
Thank you. Have a good day.